Recording in progress.
All right, we'll get started here. So we got quiz question number 8. And then I want to look at some video clips to show you, because you got some visual learners, plus you just got to see the visualization of some things here. So we'll go to number 8, and we'll find in number 8 here. Typically, there's a question about the lab final for everybody. Nobody, unless something has changed, there should not be a face-to-face lab final. I know there's going to be an electronic survey / final quiz or something like that for some. So should not be a face-to-face, an actual face-to-face final that I know of, and I'm pretty sure that hasn't changed. All right, we're going to look at number 8 here. So let's see, let's follow writing out our Lewis structures, and that is on page 24. So now estimate hydrogen phosphorus hydrogen bond angle in pH 3. Now, oops, I spelled the word estimate wrong, but so we've got here number 1, write the skeletal structure. So we can do that. We'll just go like this. We've got 1 phosphorus and we've got 3 hydrogen. So we can do something like that. But number 2, count the total valence electrons. So count the total valence electrons. So for phosphorus, my valence electrons for phosphorus is 5, because we're in group 15, right? So phosphorus, we have 5 valence electrons. And for hydrogen, 3 times 1, so we have 3. So our total valence electrons here is 8, right? Okay. So we will put a bond. The next thing is to put a bond between our central atom and our terminal atoms. So that is step 3, draw a bond between the central atom and each surrounding atom. So we did that. The next step, place lone pairs of electrons about each terminal atom to complete their octets. Octet is 4 electron pairs or 8 electrons. Hydrogen can only have 2 electrons. So we're not going to add any electrons around hydrogen. It can only have 2. And each hydrogen has 2, right? So hydrogen's happy, just like the noble gas, helium, 2 valence electrons. Step 5, if there are more electrons left, place them as lone pairs on the central atom. Well, we have 6 electrons, we need 8, we've got more electrons left. So we're going to do this. Now that gives us how many bonding domains and non-bonding domains? 3, 1, right? 3 bonding domains, 1, 2, 3, 1 non-bonding domain. So if we look that up on our blue sheets, 3, 1 should get us. All right, 3, 1. Trigonal pyramidal. It's about 107.5. So approximately, what's the closest to 107.5 degrees is what we're looking for. Okay. Whatever's closest to that, because it says estimate. All righty. I don't know if I was sharing a screen on that. I think I was. Now I want to go back and forth, show you some audio visuals here, and look at our blue sheet, bonding domains, non-bonding domains. We'll get to some OWL examples today to get you into this. So I need to stop share and I want to get to this screen. And this is right here. Let's share this. Okay. And we're going to look at molecular shapes here. Probably get a commercial, who knows?
This screencast is on molecular shapes. The arrangement of pairs of electrons around the central.
So as these rotate, remember bonding domains, it doesn't matter. It's a double, triple, or single bond. It counts as one bonding domain. So this is CO2. Carbon is the central atom. Oxygen, oxygen, double bond, double bond. So the bonding domains on the central atom of carbon is 2.
Atom. Molecular shape. Pairs of electrons around the center.
Okay, so this is the Lewis structure, carbon dioxide. Again, the bonding domains is 2, 0. This 2, 0, these are all linear. Now, remember, and you're gonna do this for lab, we talk about the molecular shape and the electron arrangement. The electron arrangement is if all these electrons on the central atom could possibly bond, what would that look like? But all of these here are 2, 0. 2, 0 on the central atom, which makes it linear. Okay, on the central atom here. Now notice boron does not obey the octet rule. We only have 6 electrons around the central atom. So that would be referenced as an exception to the octet rule. But this carbon here has how many electrons around it in the middle? 8, right? And all of my oxygens here have 8, 8. Everybody's happy. The bonding domains here is 1, 2, 3. This is a 3, 0. Trigonoplanar for all of these. 3, 0. Trigonoplanar.
Pairs of electrons. And pairs of electrons, double bond, that result just mixing the atom in one negative trigonoplanar.
Okay. So all of these right here, the bonding domains, 2, 1 non-bonding domain, right? These are all 2 1s. 2 1s for molecular shape gives you a bent. For the true molecular shape, we say it is bent. But if this pair right here was bonded, the possible bonds that you could have around the central atom, the electron arrangement is really a 3, 0 trigonoplanar. 3. Again, think of the electron arrangements as what are the possible bonds you could do, and you could have 3 here. So the electron arrangements, again, include all the possible bonds. So these are bent shapes and they look bent, right?
So results in a bent molecular shape structure to make an ammonium.
All of these right here, 4 zeros.
All of these have 4 pairs of electrons. And each of the electrons.
So all of these are tetrahedral as they're spinning. I'll show you that under the document camera in a sec. All of these right here, the true molecular shape is a 3, 1, 3, 1, 3, 1. So the true molecular shape is a 3, 1 trigonal pyramidal. The electron arrangement, it could have 4 bonds. And when you do the electron arrangement, you're never considering non-bonding domains. This is a 4-0. So it's going to be a 2-0, 3-0, 4-0, 5-0, 6-0. It's always the 0 that you'd be looking at on the blue sheet. So these are all 3 1s.
It still has to be 4.
For bent here, we have 2 bonding domains, 2 non-bonding domains. So this is 2-2, this is bent. But the electron arrangement, you could possibly have 4 bonds here. And a 4-0, we always say is tetrahedral.
As to the terminal caves.
All right, look at these babies. As you look at this one right here, and we'll see some more examples of this, look at this middle section that rotates. As this middle section rotates, what is the bond angles between these middle 3? This one, and this one.
This is sulfur. Why? What is the shape? That's that.
This is 120 degrees in the middle. 120, these are 120. These are 90 with each other, huh? 120 and
This
90.
5 pairs.
Now this right here is a 5-0.
Have 4 of those pairs.
This right here would be a 6-0.
Have 6 pairs. Now, thank you for watching this screen test.
Okay, let's look at this now. I want to start with what we did last time. We did a CH4, and I'm going to stop. I'm going to go on my other screen here. Here's my CH4. Now, no matter which way I rotate this, and this is what I said last time, be careful. This is a 3-dimensional shape. When you look at something like this on a sheet of paper, you draw it out like this. And then you say, oh, that's easy. All those bond angles are 90 degrees. No, 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 no. In 2 dimensions as you're looking at it, yes. Now, I won't get into drawing that in 3D yet. We'll do that at another time. But in 3D, in 3 dimensions, then, no matter which way I flip this, this is exactly the same. This is a 4-0. This is a tetrahedral shape. What's my bond angles? And you can kind of look at it like this as I project it in 2 dimensions on that screen. Straight out right here would be 90, huh? So we're over 90. This bond angle right here is 109.5. Okay, 109.5. Now, what does that look like? So again, if I rotate this, and if I click on my electron geometry is going to be a 4-0 tetrahedral and my molecular geometry. And if I show the bond angles, 109.5. Now, what we're doing is called valence shell, VSEPR, valence shell electron pair repulsion theory. So non-bonded electron, so when I go to a non-bonded electron, similar to this, I'm going to go to a 3-1. Look at what happens to the bond angle. It goes tighter, right? From 109.5 to 107.8. My electron pair geometry is tetrahedral because I can have another bond up here, correct? So 4 bonds. My electron pair geometry, 4. Tetrahedral. What is my true molecular geometry? Trigonal pyramidal, right? 3-1. 3-1. Okay. Now, let me comment on this bond angle here being reduced. So if I take this if I take this pair of electrons off and replace it with a non-bonded pair. Now, if I've got another bond on here, think of it this way. You know there's a positive nucleus here, correct? So you would think that this bonding pair, it would make logical sense that that is kind of streamlined as that negative charge is attracted to the positive nucleus on this atom and to the positive nucleus on this atom. But when I take a pair of electrons away and replace it with a non-bonded pair, all that negative charge up there expands out and it is going to repel these pairs. So as I try to illustrate this, I'm going to say these are going to repel down or tighter, closer together. 109.5 like this, down to 107.8. And if I go even farther to the next one, water. Look at this. So here's water. Again, if you look at this, you think this is a linear molecule, especially with what's on the blue sheet, but that's not right. Think about this in three-dimensional space again. So what is our electron geometry? We could have 4 bonds on this, right? Because what is the molecular? The molecular geometry is a 2-2. No doubt, 2-2. We've got 2 bonding domains and 2 non-bonding domains. So my electron geometry is 4. I could have 4 bonds. My true geometry is 2-0, but look what happens to my angle. So I went from 109.5 in this to 107.8 in this due to this electron cloud to 104.5. It's even repelled closer together, right? Even repelled closer together. So this is my water again, 2-2. Okay, if let's see, here's carbon dioxide, linear molecule, right? Linear molecule. 2 double bonds, we will do that. Okay, let's look at this. This is, the bond angle is 180 degrees here. This ends up being linear molecule, correct? Straight across. These are 3 non-bonded pairs. So what is my electron geometry? My electron geometry is 5 possible bonds, right? And if you go to your blue sheet, you look up a 5-0 and it'll say trigonal bipyramidal. What's my true molecular geometry? Just linear. It's all in a straight line. Oops. So what did I just do there? All right, BF3, this is linear because boron only has 6 electrons around it in the central atom. Again, this is an exception to the octet rule. So let's say linear, this is 120 degrees, but this works in 2 dimensions. If you draw this on the paper, piece of paper, it is the same molecule at 120. So trigonoplanar, trigonoplanar. Bonding domains here. 1, 2, 3. This is a 3-2, correct? This would be a 3-2 for molecular geometry, which would be T-shaped. But how many possible bonds for electron geometry? 5. This right here would be a 4-1. But again, we could have possible for electron geometry, 5 bonds. Five, 1, 5 bonding domains. There's 5, 1 non-bonding domain. But what's our total bonds we could have? 6, right? If we have 6 bonds, we have octahedral, which should be the next. Not the next one, but here's a 5-0. So as I rotate this, these middle 3, 1, 2, 3 are 120 from each other. If I rotate it this way, think about the x-axis being here. I'm rotating the x-axis. As I rotate the x-axis, those 3 would be 120. But these are 90. Between my y-axis and my x-axis would be 90 degrees, right? So this right here is a 5-0. And the very last one gets us all 90. So if I rotate it this way, these 4, think of these 4 in my x plane. So these, if I rotate it this way, are all 90, right? All 90 in my x plane, and then between my y and my x. So everything's 90 here, correct? So this would be a 6-0 octahedral. Okay, let's switch back to my document camera. So be careful, because I said here, if we look at water on our blue sheet, H2O, water should be a 2,2. I think we get to it coming up. 104.5. But if you look at this, it looks like it's linear. If I put a non-bonded pair on top, non-bonded pair on the bottom, it looks linear. But it's really this. As I take one more away, there's my bent shape. And again, these are going to be repulsed tighter together. We're down, we get to 104.5. Okay. Carbon dioxide. We'll look at this more in a bit. All right, I want to probably right now do a little bit more in our learning guide from the beginning, because it goes through some OWL examples. Then we'll go back. We have to do some more Lewis structures as well. Okay, so we talked about sure I'm on the right one. Okay, so we talked about a metallic bond being this concept. They usually refer to it as a sea of electrons. Okay, then if we have ionic bonding, the best thing for ionic bonding is we talk about electron transfer. And for that to happen, sodium wants to get rid of its 1 valence electron. What valence electron is this? This is a 3s1 valence electron. All right, here's my sodium. It ends in 3s1. It has 11 electrons as a neutral atom. If it gets rid of 1, it has 10 electrons, just like the noble gas neon, right? That's our goal here. Then if we have chlorine, chlorine is a 3p5. Not 3p5. Yeah, 3s2, sorry. 3s2, 3p5. How many valence electrons? 7, correct? 7. So what's it need? It needs 1 more electron. And if it gets that 1 electron, it goes from 7 valence electrons here to 8, just like the noble gas argon, right? So that's what we do. We say, whoa, sodium gets rid of that 1 electron. It's now a +1 ion. Chlorine takes that 1 electron. It's now not chlorine. It is chloride. Okay, so we use this concept in ionic bonding. We say it is electron transfer. And we talked about reducing agent and oxidizing agents and so on. But what do we end up with? Noble gas. Electron configuration notation. Now, covalent bonds. For covalent bonds, we say sharing electrons. In most chemical compounds, electrons are shared unequally between atoms, with the extent of sharing varying widely from mostly ionic to little sharing, which we call ionic, to considerable sharing, mostly covalent. We'll look at that more closely. All right, covalent bonding in Lewis structures. So this comes from the American chemist Gilbert Newton Lewis. And valence electrons, we said, are group numbers, right? Group 1, group 2, but then the ones place. And we went right into an example of Lewis structures to get you started. So if we have calcium here, it should be electrons. It says, draw the atomic symbol. This represents the atomic nucleus along with the core electrons. So if I draw the atomic symbol, and I will do that for calcium right down here, this is when we do electron Lewis structures, and you've already noticed that we have a central atom. And typically we do something like this, right? We put 2 electrons here. This would be a complete octet, right? That's what we're trying to do most of the time, but this is all single bonds. In this case, if I put down calcium, Ca for calcium, the atomic symbol represents the atomic nucleus along with the core electrons. What are the core electrons? The non-valence electrons. Treat each side as a box that can hold up to 2 electrons. Count the electrons in the valence shell. Start filling boxes. Don't make pairs unless you need to. So if I did calcium, typically, it doesn't really matter. I would do 1 at the right, 1 on top. So again, the symbol though represents the non-valence electrons. What I just did is my 2 valence electrons. There's my core electrons here in yellow. So you kind of do this, well, you do this like Hund's rule. We're going to put 1 electron in each before we come back around and pair them up. So here's the Lewis structures for main group elements. So this is group 1, group 2, groups 13, 14, 15, 16, 17, 18. And the reason I do that is this is not consistent. This might be an A, but then they'll go 3B in a different book. Let me take this light off, see if it's better. So group 1, group 2, then our valence electrons again, groups 3, 4, 5, 6, 7, 8. That's our valence electrons, right? So everything in group 1, lithium, sodium, 1 electron. We'll put it there. There, I think that's a little better. Group 1, 1 electron. Group 2, 2 electrons. Here they put it on the side to side, which is fine. Group 13, 3 electrons. Group 14, 4. Group 15, 5 valence electrons. So this is like Hund's rule, right? We're kind of putting 1 around it. Now we're going to start pairing them up. Okay. I think this is an question. Maybe not. Which of the following is not a correct Lewis structure? And when you say correct Lewis structure, typically we're looking for the central atom to have 8 electrons, typically. So does this central carbon have 8 electrons? 4 bonds, 4 times 2 would be 8 electrons. So this is okay. This nitrogen has 8 electrons around it. What do we got here? And this chlorine has 8 electrons. I should say that too. Oxygen has 8 electrons. This oxygen here has 8 electrons. This oxygen has 8. This nitrogen here has 8 electrons. This oxygen, 8 electrons. Hydrogen has 2. This looks good. Oh, what do we got here? Ooh. I don't know what the heck. We got 10 electrons. We got lots of junk going on there. Let's just say junk on this. Huh? We got 10 electrons. We got oh man. All right, let's go to the next page. I think at this point, we can draw this, we can figure this out. We touched on Lewis structures last time, got our feet wet. So let's look at this owl here. And must not be too ugly because I put not so ugly. From the Lewis structures of the species given, pick all of those which the central atom obeys the octet rule. So if it obeys the octet rule, the central atom should have 8 electrons. 8 electrons around the central atom. All right, so we only care about the central atom. So what do we got here? We've got 4 electrons there because there's 2 pairs, right? 4 electrons. 6 and 8. Pick all of those, which, okay. So I'm going to pick this one for sure, correct? That's 8 electrons, central atom. For the next one, this is 2, 4, 6, 8 on the central atom. That looks good. The next one on the central atom. So we have 2, 4, 6, 8, 10 electrons, right? 10 electrons. We're not going to check that one. Let's go back. 8 electrons, right? And this central atom here has how many? 4, right? This is 4 electrons. So when we're doing we're only going to like those first 2, huh? All right, let's do, let's do this not so ugly owl as well. It says to answer the questions, interpret the following Lewis structure or Lewis diagram. Okay. Let's see what we've got here without drawing this out from scratch. For the central xenon atom, the number of non-bonding electrons is 2. It's not pairs, but those are not bonded, correct? The number of bonding electrons is 6 bonding electrons, correct? The total number of electrons around the central atom is 8, right? 2, 6, 8. Then the central xenon atom obeys the octet rule, has more than an octet, has less than an octet. That's nice. We got 8, right? So it obeys the octet rule. That would just be an A, huh? Okay, I do not want to do formal charge yet, as I want to probably do a little bit more on Lewis structures first. Al does a lot with molecular shapes to get you started, and I've got them on page 6. Now, I'll freely admit I've got too much stuff here. I'm like trying to cut this down. Oh, I don't want to cut this, so I'm trying to cut this down a little bit. Now, here's our molecular shapes, 2 pairs of electrons, linear. I would call this two, 0, linear, 3 pairs of electrons, 3, 0. 4 pairs of electrons, we know is going to be tetrahedral. Trigonobipyramidal, 5, 0, and octahedral, 6, 0. Now, there is quite a few videos here. So if you open up this learning guide, you can click on this. There is quite a few videos. And Page 7 looks at the 4 pairs that we could have for electron geometry. So if we have 4, 0, we get tetrahedral. 3, 1. And then 2, 2. So 4 electron pairs. 5 electron pairs here. So this 5, 0. This right here is a 4, 1. 3, 2. And then a 2, 3. This is bonding domains, non-bonding domains. Now, the electron pair geometry does not change. Electron pair geometry does not change. Right, all of these, you just think it could have 5 possible bonds, so they'll describe the electron pair geometry is trigonal bipyramidal. Up here, the electron pair geometry does not change, tetrahedral. On the next page, if we go to 6 possibilities, the electron pair geometry does not change, octahedral. So this is a 6, 0, 5, 1, and a 4, 2. Okay, let's do this. Let's go to the last. Let's do another Lewis structures on our Lewis structure page here. We left off. And actually, I want to do the CO2. Let's look at this for the CO2. So the compound, we have carbon dioxide. Let's do our total valence electrons. So carbon should have how many? Carbon's in group 14, so we got 4. Oxygen has 2 times 6. So we're looking at 16 here, huh? All right. So skeletal structure, total valence electrons. The next step, step 3, is to draw a bond between the central atom and the terminal atom. So we'll draw a bond between the carbon and the oxygen. Then the next step is to complete the octet of the terminal atoms. So we're going to have to add 6 on each of these oxygens. Okay, so my total electrons I put down so far is 16, correct? I've got 16 electrons here. How many electrons am I allowed? 16, correct? But we have a major problem. The central atom carbon only has 4 electrons, correct? All right, so let's see where we're at here. We did 1 through 4. Let's look at this. 5 says if there are more electrons left, there's no more electrons left, correct? We've got 16 electrons down. We're allowed 16. We're going to skip. There's no more electrons left. Let's go to step 6. If the central atom has an incomplete octet, yes, yes, yes. That's what we're talking about here. Use the electrons from surrounding atoms to make double or triple bonds. Do not add electrons. Borrow them from other atoms to make multiple bonds. A double bond is going to be 2 pairs of electrons, triple bonds, 3 pairs. Only these are going to form multiple bonds. So we're going to borrow. In this case, I'm going to borrow a pair here, and I'm going to borrow a pair there. So what is that going to look like? It's going to look like this. We're going to talk about resonance structures next time we meet. So we've got our first multiple bond compound. We had to borrow them from the terminal atoms, correct? We just borrowed them. So what is my bonding domains here and non-bonding domains? Now, all right, my table here must not have went perfectly. Oh, do I have electron? Yeah, I do have electron pair geometry. My bad, it does. All right, so we have 2, 0. What is my hybridization on a 2, 0? Check your blue sheet. We'll talk more about that. SP. What is my electron pair geometry? Or my, it's going to be linear. My molecular geometry, and my electron pair geometry is a 2, 0. My molecular pair geometry is a 2, 0. Linear, 180 degrees. All right, on the quiz, try 1 through 15 on the quiz, poke around in OWL. 1 through 15 on the quiz. Remember, for a negative charge, you have to add a valence electron. For a negative charge, I think there might be 2 within that. You have to add 1 valence electron for a negative 1 charge. All right, have a great day, everybody.